Welcome to another MDP&P webinar. Today's topic is OpenICE, a technical introduction. My name is Jeff Plord, lead software developer at the MDP&P program. Assisting me with this presentation was Jeff Peterson, clinical engineer at the program. Our agenda for today will include who is the MDP&P program, what is OpenICE, an overview of the system architecture of the OpenICE platform, how that fits into parallel and distributed systems generally, use of the data distribution service standard in the platform, and then a brief dive into the data model used. The Medical Device Plug-and-Play Interoperability Program is promoting innovation in patient safety and clinical care by leading the adoption of patient-centric integration of medical devices and IT systems in clinical environments. Our program attacks the problem of medical device interoperability on a number of fronts, including, but not limited to, regulation, industry adoption, the demonstration and, more importantly perhaps, documentation of clinical needs and pull from the clinical community, the development of applicable and the application of existing standards, as well as the development of prototype platforms. OpenICE is one such platform that has been developed by the program. So let's take a step back for a moment. Before there was OpenICE, there was ICE. The acronym ICE stands for the Integrated Clinical Environment, which is described in ASTM standard F2761. The program helped lead the development of this standard to provide a common language or nomenclature for describing interoperable systems of medical devices. The standard also lays out functionalities required of such a system and assigns actor names to different groupings of functionalities. OpenICE is an open source community-driven prototype implementation of the standard for the integrated clinical environment. It is one component of the work of the MDP&P program, and it helps the program to both learn and to teach about interoperable medical system devices. The constituents of the platform include interfaces to myriad medical devices that are available in the MDP&P Interoperability Lab in Cambridge, Massachusetts. So in that lab, we've developed software to interface with a number of these devices, and we include those pieces of software as part of the platform. We also include software-based simulators of various medical devices, and this is for the use of those people out in the community who may not have direct access to medical devices. We also include in the platform supervisory software, as well as some examples of clinical applications, which are meant to inspire and invoke the creativity of the community in adding to that library of applications. A convenient example of the platform at work we've put together at openice.info. So this diagram shows that in our lab we have continuously operating a patient physiological monitor and an ICU ventilator running our platform software on small single board computers known as BeagleBone Blacks. They are interpreting that information and delivering it to the platform at large. For this particular demonstration, we have a Node.js application tapping into that middleware and displaying that data on the web. So more generally, let's discuss what a parallel system is. A parallel system includes multiple processors running multiple software programs concurrently within the context of the same computer. So you see this every day in your everyday use of computer systems, in that you have an email program, perhaps a web browser, a word processor, and they're all sharing a common system memory. And the distinction when we get into distributed systems is that the nodes of this distributed system do not share a common system memory. In this case, the only way that computer nodes of the network can find out about the state of other nodes is by sending messages. As a consequence, no one computer or computing device can know at any instant the true contents of all the isolated computer memories. So this is just demonstrating the problem. In the first line of this slide, you see kind of a current state, a pulse oximeter reading a pulse rate of 65, a capnometer reading a respiration rate of 12 breaths per minute, and an application that is unaware of both of these values. So in the current state, the measured pulse rate is 65, the measured respiration rate is 12, and yet the app knows nothing of either of these pieces of information. And then you can see at another point in time, when the message arrives from the pulse oximeter, the app knows a condition where the pulse rate is known of 65, but respiration rate is unknown. And then at another point in the future, when a message is received from the capnometer, now the app kind of knows the full true state of the entire system. There are a number of examples of middleware that can help with the delivery of these messages. Developing a system on a message-oriented middleware can be a very complex thing to do. This is not a natural analog to a parallel system because there's no shared common concept of system memory. Instead, messages have to manage this complexity of relating different state information from nodes back to one another. So what is the data distribution service? The data distribution service is a standard for an API that simplifies distributed system development. And the way that it does this is by replicating or producing a synthetic shared memory across the entire system. So in this case, the medical device and the application can both perceive or interact with the same global memory space as if they were running on the same computer. What DDS does below the surface is exchange messages to ensure that every participant in this system perceives or sees the same system state. So here you can see in the OpenICE prototype, device adapters are interacting with this common system memory or data model, as well as a supervisory application, a web server perhaps, and in our lab we even have a data logger recording the data that's shared with this data model through time. And now you'll see that this maps directly back to the previous slide. So this is what's going on kind of beneath the surface of that demonstration that you can see at openice.info. So DDS, why have we chosen it for use in the MDPMP program at this time? First, it's a standard. It's not only a standard, it's an open and vibrant standard with a community of companies and individuals interested in its further development. It also supports multiple languages such as C, C++, Java, Scala. There's always a new language that's adding support. DDS is vendor neutral. The OMG standard can be downloaded by anyone and implemented. There are several companies that develop DDS middleware, and there will probably be more in the future. There's also an open source implementation known as OpenDDS. Another feature of DDS that we find incredibly useful is the declarative non-functional characteristics. These are known as quality of service policies in DDS. So as you've seen in a previous slide, DDS presents a common data model to every participant in the system by exchanging messages. The way that those messages are exchanged and the non-functional requirements that need to be met by those messages to ensure that the application sees the same system state as each device, those are controlled by these quality of service policies. So rather than having to rebuild the system to change those non-functional characteristics, they can be configured. Also, DDS imparts interoperability. It uses a very familiar data access paradigm that people can pick up and plug into. So these are some examples of what a quality of service policy might look like. Reliability, for instance. On most computer networks, information can be sent, but there's no acknowledgement of that information that's built into, for instance, an Ethernet or an IP network. So as an option, DDS can enable reliability, which means when a device sends a piece of data or information, that information is then acknowledged by the receiving application or supervisor. If the acknowledgement is not received, retransmission can occur, and another attempt can be made. And within the context of policies, limits can be put on how long you can wait for acknowledgement of a message and how many times you can retry. Another important policy is liveliness. This means that if you're reading data from a device and you want to know that that device has disappeared from the network, that can be controlled with the liveliness quality of service policy, setting an upper bound on how often a device has to communicate that it's still on the network. Another important policy is destination ordering. So the underlying UDP/IP protocol used by DDS does not guarantee that information arrives at the receiving entity in the same order that it was sent. So DDS allows you to configure it to provide that ordering. So any one of these policies would require a great deal of implementation if it was built upon a message-oriented substrate. In DDS, it's merely a matter of configuration. DDS has somewhat its own vocabulary, and I'm going to describe some of the terms that are used in DDS. This will allow us to discuss briefly the DDS data model used in OpenICE. A domain is the largest scope of DDS. It represents an isolated communication plane on the UDP/IP network. Traditionally, we use domain 15 for OpenICE. A participant is the DDS term for any entity that announces itself on a network and can discover other entities and itself be discovered. Often this would be a medical device or an application, but it could be many, many other types of participants or entities. DDS is a strongly typed middleware, and those types are defined with interface definition language. So these types define the structures of the data that are shared on the network. The structure of the data model must be defined before the system is compiled. Participants are looking for data, and the type is how they know what they are looking for. Topic. In the DDS publish-subscribe middleware system, topic is merely a string, but it's more than that. It's a rendezvous point so that publishers to the system can find associated subscribers. So if I'm a publisher of device identity, I would identify that as the topic to which I'm publishing. And if I'm interested in the identity of devices, I would subscribe to that topic. And in this way, we'd find each other on the network for data exchange. DDS has a special feature that each unique occurrence of a topic is termed an instance, and it's identified by a primary key. So you can see some examples here. For instance, the inspiratory time period from a Draeger Evita XL ventilator, measured in seconds, constitutes one instance of the numeric topic. So if new samples were to arrive, they would replace the most recent sample for this instance, but we would know that that's not related to a different instance, such as the inspiratory tidal volume or the inspiratory part. As I've mentioned before, samples are the actual data values that arrive for each instance. Partitions are a logical way to divide a DDS domain. The possibilities that are provided by partitions are innumerable. At this time in the OpenICE system, we're using them for patient identification, so that each patient's data is present in a separate logical partition from other patients. As in many other middlewares, DDS has a publisher and subscriber concept. Although in DDS, what's traditionally called a publisher is actually called a writer. So a writer is a provider of data samples to the system. So for example, a data writer living in a ventilator could be publishing airway pressure to its associated topic instance. The DDS term ultimately for a subscriber is a reader. This is a consumer of information, the entity used to access or consume data samples. So as a corollary to our writer of airway pressure, we may also have a reader that receives these samples. This might be a clinical application or a supervisory app. So now we'll get into some of the particulars of the OpenICE data model developed with DDS. OpenICE system components are obliged to read and write the data model in a prescribed way, and that prescription has several parts. The first, as we've discussed, is the IDL definition of data types of samples that will be published in the system. The second is the name of the topic at which those samples will be published. Also, there must be a certain matching of QoS policies. And also there must be a shared concept of what it means to have a topic instance registered for each topic. And I'll get into that in more detail when we get into the specifics. The first topic I'll talk about is the device identity topic. This exists because a device must furnish identifying information to the rest of the OpenICE system. This information doesn't change, and therefore the instances are allowed to live indefinitely. Another topic is device connectivity. So often in the OpenICE system, medical devices cannot natively connect to the system, so there'll be an intermediary. We often use the BeagleBone Black for this purpose as a bit of a protocol interpreter. So where those further connections exist, the BeagleBone Black in this case would need to communicate whether it has achieved a connection to the device itself, and it communicates that information to the rest of the system with the device connectivity topic. A heartbeat topic is used. The contract here is that every participant in the OpenICE system will publish a heartbeat at least every 2 seconds. So any other participant that wants to know about all the others in the OpenICE system can observe heartbeats and look for live heartbeats. Time sync is a topic that's used to ensure that time is being synchronized across the OpenICE system. This is not used for correction of time. For that, we're using network time protocol. This is a double check to ensure that we're seeing at runtime synchronized clocks. The numeric topic is for expressing sensed data that occurs at a pretty slow rate, generally less than 3 Hz. You can see more information about the data model here, but you can think of the numeric topic as sharing the big numbers that would occur on a medical device screen. And the sample array topic is for data that are sampled much more quickly by their sensor. You can think of these as waveform tracings on the display of a medical device, and this topic allows for the sharing of that much more high-frequency data. So that ends our technical introduction to the OpenICE platform. For more information, there are a number of websites that you can visit. Thank you very much for tuning in.